Hi, good day dear audience. I was arguing with my wife by the way how one can hang clothes and make them dry as quickly as possible. Of course I am not intruding with her work or the house work, but this is my specialization. Not the housework, of course. My specialization is thermal engineering, including hydraulics, thermodynamics, and anyhow, whatever. So the question was as follows. You have a rope, that's the supports, and this is the rope. Is it better to hang the clothes nearby, like this, on the rope, or it is better to, that's the supports once more, that's the rope, and these are the clothes. Excuse my drawing. Of course the closet doesn't look this way, of course. Or it is better, if you have space, of course, to hang them with a spacing between them like this. Of course, this way leads to quick drying. This takes more time to dry, perhaps more than twice, yes, perhaps much more. Why? That's the question. Let's discuss that. Of course, the more the difference in concentration of whatever this item is, whether it is a material or it is temperature, the concentration variation between the body dispensing or losing something and the concentration of the media, the quicker it loses this thing. Supposing this is body at hot temperature and this is the ambient here. If this is very hot, it loses heat Q in joules or in calories, whatever, quickly. It loses more joules or more calories in a unit time if this is at high temperature. Similarly, if this is at high temperature, what if I made the temperature constant and make the ambient lesser? The same. It depends on T body minus T ambient or TS surrounding. The more T body minus T surrounding, the greater the loss of this quantity. Whether it is joules or whether suppose this is a piece of cloth, porous, containing droplets, and here lesser concentration of droplets surrounding it. It will lose the quantity of what is contained in it quickly. If there is high concentration here, let's make this constant, the amount of wetness or the amount of water contained in the piece of cloth. The more the lesser the concentration of water in the surrounding, the quicker it loses its water or its wetness content. That's the point. So this is why if you put clothes apart, because every piece of clothes makes the ambient, interacts with the ambient to make a curve like this. It is an E-curve, e to the power minus, forget about the mathematics. This piece of cloth and that one intersect here. Supposing this is, the curve is the dropping of the curve, the fall down of the curve resembles the temperature. So they will meet body and T surrounding here. But if they put them nearby like this, you will start drawing the curve here and here. They would not have enough distance to fall down like at this low temperature here or at this low concentration, whatever it is, wetness or temperature or whatever. So that's why. So now let me write the formula. How much time is needed for a single droplet to get evaporated? T is given by, if you want, I can make a separate video on its proof, how this formula is was obtained. T equals rho D original square over 8 lambda len. That's the natural logarithm, of course. 1 plus CO minus C infinity over 1 minus CO. Through density, d droplet diameter, lambda the diffusion coefficient. We wish to explain every item in separate. I don't like to be putting meaningless items, of course. Rho, that's the density. Everyone knows density. It's mass m per volume, cube of length, kilogram per meter cube. In MKS system of unit, of course, the diameter would be expressed in meter. If it is in millimeter, 1.5 millimeter, for example, so its diameter would be 1.5 times 10 to the power minus 3, because this formula is in the meter kilogram second MKS system of units, meter kilogram second system. That's it. Lambda, that's the diffusion coefficient. Units is mass per length times time, kilogram per meter second. What is C? C is the concentration. C is dimensionless. How can be dimensionless? Yes, it is dimensionless. How and why? Because in this formula it is considered as a ratio between C, the ratio between somewhat like density, amount of mass or quantity, it could be temperature, but in our case it has the same unit of density, mass per volume at the present or instantaneously, compared to the mass over the maximum mass this volume can hold. So it is m over I instantaneous or at present to mass over volume in general. So this is C. So here C, this is the original concentration at the surface of the droplets. C infinity, the concentration at the very far distance from the droplet, as you wish. Okay. 1 minus CO, then the concentration at the surface of the droplets. That's lambda. So this formula is logical. Why? This formula, if you want to find the time when the droplet diminishes, for example, from 2 millimeters to 1/4 millimeter, I put the instantaneous diameter here square. But this formula is made to calculate the time taken for the droplet, so it vanishes completely evaporates, not to find when it would reach another. But if you wish, you can put here and find T in case of another diameter, when it changes diameter, for example, from 2 millimeters to 0.5 millimeter. So, but here our intention is to find the time to completely vanish of the droplet, of a given droplet, because if one droplet vanishes, most of the droplets would vanish. Tell me, but the droplets are near each other. Yes, this gives a general idea how the effect of ambient concentration works, and give a near idea, very near, but to solve a given piece, wet piece holding numerous droplets, when exactly, because they every droplet create a concentration on itself with nearer droplets. It can be solved on a computer, of course, but this gives a very near idea how much time is taken. That's our formula. Solve it yourself for a given droplet, let's say of a diameter droplet of 2 millimeters, of 1.5 millimeters, and see how much time it takes using this is in seconds, of course, not hours, because we are using this is in kilogram per meter cube. Water, it is 1000 kilograms per meter cube. Rho, of course, that's for water, 1000 kilograms per meter cube. You take rho 1000, take the diameter, original diameter, 1.5 millimeters times 10 to the power minus 3 to make it in meters, okay? Lambda, of course, this is the diffusion coefficient. It's not constant all through, but it varies with temperature, with pressure, atmospheric pressure. That's for water. Lambda, take it in solving your problem to be, it varies from 4 to 28 times 10 to the power minus 6. 4 times 10 to the power minus 6 or 20. It varies according to the temperature, the amount of water current, of air currents. The more the air currents, the more you get near the 28. Or It's sometimes it reaches 30. Okay, something missing. C take it to be 0.027. Now you can calculate it yourself. See how why. Consider that 1 meter cube of clothes can hold, not dropping water, wet, can hold 27 kilograms of water. So see, as I said, it is the ratio between the present mass, the mass present in 1 meter cube to the maximum. So pounds per meter cube. You take rho 1000, take the diameter, original diameter 1.5 millimeters times 10 to the power minus 3 to make it in meters. Okay. Lambda, of course, this is the fusion coefficient. It's not constant all through, but it varies with temperature, with pressure, atmospheric pressure. That's for water. Lambda, take it in solving your problem to be, it varies from 4 to 28 times 10 to the power minus 6. 4 times 10 to the power minus 6 or 20. It varies according to the temperature, the amount of water of air currents. The more the air currents, the more you get near the 28, or it's sometimes it reaches 30. Okay. C take it to be 0.027. Now you can calculate it yourself. See how why. Consider that 1 meter cube of clothes can hold, not dropping water, wet, can hold 27 kilograms of water. So see, as I said, it is the ratio between the present mass, the mass present in 1 meter cube to the maximum. So it would be, so see, you can calculate it yourself. So imagine that 1 meter cube of clothes can hold, while wet, not completely immersed in water, can hold 27 kilograms approximately. Can hold 27 kilograms in 1 meter cube. While the maximum 1 meter cube can hold is 1000 over 1 meter cube. So the result is CO would be 27 over 1 over 1000, or 27 over 1000, which is 0.027. So use CO to be 0.027. Lambda, take it, for example, 15. So, see, you can calculate it yourself. So imagine that 1 meter cube of clothes can hold, while wet, not completely immersed in water, can hold 27 kilograms approximately. Can hold 27 kilograms in 1 meter cube. While the maximum 1 meter cube can hold is 1000 over 1 meter cube. So the result is CO would be 27 over 1 over 1000, or 27 over 1000, which is 0.027. So use CO to be 0.027. Lambda, take it, for example, 15 times 10 to the power minus 6. C 0.07, as I said, CO. C infinity, take it to be 0.001. C infinity, 0.001, or make it 0.0013 in case of wet ambient. So C infinity varies with how much the ambient is wet. For example, if you put the clothes near, C infinity would be 0.02, 0.015, 0.018. If the clothes are apart, C infinity would be 0.001. So, and calculate it on the calculator yourself. Hope that's interesting. And if you want a separate video on how this formula is derived, it's so simple. I can present it to you. Okay, bye, my dear audience. Once more, I am not intruding with the house